We're going to continue our talk about the second derivative. We'll discuss concavity and the second derivative test to find where concavity switches between concave up and concave down. We'll start with concavity. Concavity is basically the shape of a graph. So you can see I have a parabola that's kind of U-shaped, which is x squared, and then I also have the reverse of that, negative x squared, which is concave down. So the next two I have here are the natural log of x and e to the x. And let me label that for you. This is the natural log of x. This is e to the x. Now what's interesting about these two functions is if we stuck with what we've been talking about, like increasing, decreasing functions, both of these functions are increasing. Natural log is going up, e is going up, but they're doing it in much different ways. Natural log of x is concave down. E to the x is concave up. And hopefully what you see is that the natural log of x is growing much slower, so it's increasing at a decreasing rate, where e to the x is increasing very quickly, it's increasing at an increasing rate. And a lot of that comes from the concavity. That shape helps us see how quickly something's changing. Now, concavity could change throughout a function, so it doesn't have to just be up or just be down. It could change. So let me show you another function that's a little more complicated. So you can see this one went up, it went down, it went up, it went down, it went up. So what do I have? I have different concavity. It started concave down, and then it switches to concave up, and then it's concave down again, and then it switches back to concave up. So when we have more than one type of concavity, it has to have a place where it changes. And the place where it changes is called an inflection point. So we're going to have to work on how are we going to find these places where we change concavity. If you remember back, we found out increasing and decreasing changed at partition numbers. And those partition numbers could be critical points or places that were discontinuities of the graph. And we're going to have similar things for inflection points, but the inflection points will have to do with the second derivative. To get us started with that, let's look at the second derivative test. The second derivative test breaks up the domain of f of x into intervals based on where the second derivative is 0 and where the second derivative is undefined. Just like we did for the first derivative, we will pick a point in each of these intervals and we'll test the sign of the second derivative. When that test point makes the second derivative positive, we know it's going to be concave up over that interval. If the second derivative is negative at the test point, then the function is going to be concave down over the interval. If the function changes concavity at a point C, then C is going to be the inflection point. Right. So we need to try that in a bunch of examples. So our first example, we'll find the concavity and the inflection points of f of x equals x cubed minus 24x squared. The first derivative is 3x squared minus 48x. We're going to move right to the second derivative, which is 6x minus 48. I want to take the second derivative and set it equal to 0. That says 6x is 48, so x will be 8. So this is where our second derivative was 0. This is where we will start our intervals. Now this is a polynomial, so the real number line is our domain. We just need to split it at 8. So we're going to go negative infinity to 8. Then we have 8 to infinity. We'll pick a point in each interval. So let's say I pick 0 between negative infinity and 8, maybe 10 from 8 to infinity, just picking really easy numbers that I can plug into 6x minus 48. If I plug in 0 to 6x minus 48, I get a negative. That says concave down. If I plug in 10, 6 times 10 is 60, minus 48 is positive, that's concave up. I can tell my functions, concave down, negative infinity to 8, and then concave up, 8 to infinity. It changed concavity when x was equal to 8, so I have an inflection point. Let's write that up here. My inflection point is 8, but I also need a y value. To get the y value, I'm going to plug 8 into f of x is x cubed minus 24x squared. It'll give me negative 1024. Our next example says find the concavity of f of x is x to the 7/2 plus 9x, and again we'll find the inflection points. We'll start with the first derivative. The 7/2 come down. When I subtract 1, I get 5/2. Derivative of 9x is 9. I go straight to the second derivative. The 5 halves times 7 halves. 7 times 5 is 35. 2 times 2 is 4. I have x. I subtract 1, that's 3 halves. The 9 is a constant. The derivative is 0. What do I have? I have 35 over 4. X to the 3 halves is 0. Now this looks a little messy because it has a fraction as a coefficient, it has a fraction as an exponent, but it really turns out that this would just be x is equal to 0. You could divide 0 by 35 over 4, you would just get 0. You could get rid of the exponent and you're still going to get 0, so why waste doing all that time? And let's just say that's 0. Because our original function, f of x, is x to the 7 halves plus 9x, our domain is 0 to infinity. This 2 from the 7 halves is a square root. I can't take the square root of a negative number, so I know my domain starts at 0. This means when I'm looking at this, I only have one interval, and that interval is 0 to infinity. I want to pick some kind of point, so let's pick something easy like 1, and let's test the sign of the second derivative. Well, if I take 1 and put it into 35 over 4 times 1 to the 3 halves, this is going to be greater than 0, so that's positive, which says this is concave up. I don't have an inflection point because it's not changing concavity at any time. Next, let's find the concavity of the natural log of x squared minus 6x plus 10, and we're going to find all inflection points. We'll start by finding the first derivative. Remember, with the natural log, it becomes a fraction. The x squared minus 6x plus 10 goes in the denominator. 2x minus 6 goes in the numerator. To do the second derivative, we are going to have to use the quotient rule. So we have low, x squared minus 6x plus 10, d high, which is 2, minus high, 2x minus 6, d low is also 2x minus 6, all over the denominator squared. Let's multiply that out, try to make it look a little bit better. 2 times x squared is 2x squared. 2 times negative 6 is negative 12x. 2 times 10 is 20. I'm going to leave the negative sign and leave parentheses. 2x times 2x is 4x squared. Then I have negative 6 times 2x and then negative 6 times 2x. That's happening twice. So negative 6 times 2 is 12, but I had it twice, so we're going to call that negative 24x. And then negative 6 times negative 6 is a positive 36. All over that denominator squared. As we continue to simplify this, I need to drop the parentheses in front of the negative 4x squared minus 24x plus 36. So I have 2x squared minus 12x plus 20, then minus 4x squared plus 24x minus 36. And again, we keep the denominator. So let's combine like terms. 2x squared minus 4x squared is negative 2x squared. Negative 12x plus 24x is positive 12x. 20 minus 36 is negative 16. Setting the second derivative equal to 0 means I really need to take the numerator and set it equal to 0. I'm going to factor out a negative 2. I get x squared minus 6x plus 8. And then I'm going to factor to x minus 2 and x minus 4. So we get x equals 2, we get x equals 4. Okay. This is a natural log, and we should have some concern about whether or not the 2 and the 4 fit into the original. So I put into Desmos x squared minus 6x plus 10. And what I want to see is when would this be equal to 0, or when would this be negative? So let's take a look at the graph. And hopefully what you see is that this is always positive. X squared minus 6x plus 10 is always greater than 0, which means any number I want to put into the natural log will be positive, so everything's okay here. I don't have any numbers I have to throw out when I'm looking at this original function. So this says both the 2 and the 4, those are good, those are in my domain, so those are potential inflection points. Why are they not inflection points yet? Because right now I don't know if it's really going to change signs there, so we need to check it to make sure. So we said we have the real number line. We have 2 points to put in, 2 and 4, that are interesting to us, maybe some potential change there. We need to make intervals, so negative infinity to 2, 2 to 4, 4 to infinity. Now let's pick some points. Let's say we pick 0, we pick 3, we pick 5. We're putting these into the second derivative. So how I'm going to do that is I'm going to take this factored form of negative 2 times x minus 2 times x minus 4, that's our numerator. And then the denominator, x squared minus 6x plus 10 squared, will always be positive because that's square. So we're testing negative 2, x minus 2, x minus 4, over the bottom, x squared minus 6x plus 10 squared. Okay, we're starting with 0. Negative 2 will be negative, x minus 2 will be negative, x minus 4 will be negative, and the bottom is positive. Negative, 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 positive is negative. This is concave down. Let's try our 3. Negative 2 is negative, 3 minus 2 is positive, 3 minus 4 is negative, the bottom is still positive. Negative, negative becomes positive, so overall, this is concave up. The last interval, I have negative 2, 5 minus 2 is positive, 5 minus 4 is positive, the denominator is positive. 1 negative makes the whole thing negative, which is concave down. Now, because concavity changed, both at 2 and at 4, we know we have 2 inflection points. Just like last time, when we want an actual point, we're going to have to plug the numbers back into the original to find the points. I'm going to give exact answers. So what I mean by exact answers, remember it was natural log. I'm just going to plug the 2 in to the natural log of x squared minus 6x plus 10. So if I plug in 2, I get the natural log of 2. Then if I plug in 4, I also get the natural log of 2. Alright, so I thought we should take a quick peek at Desmos to see what this looks like. So first off, I put in the natural log of x squared minus 6x plus 10. Then I plugged in 2 and 4 and see how the values are the same. Those are both the natural log of 2. Let me show you a natural log of 2. You can see there's the 0.693. On the graph, I want those 2 points to show up, so I asked Desmos to graph 2, f of 2, and 4, f of 4. Then when I move my screen over, you can see this is concave down until it hits here at 2. It's concave up until it gets to 4, and then it goes back down. I think for sure you can see the critical point. I think you can see where it has a minimum, but I think it's really hard to find the inflection points by eye. Like I can't really see them. I know it's switched somewhere, but really coming in precisely and saying I know it's at 2 is hard, so we need the second derivative to get our values. Let's try one with e. This one says f of x is 60 e to the x minus e to the 2x, and I want to find all inflection points. So these are kind of the same. We're going to be taking the second derivative, so I start 60 e to the x is 60 e to the x minus e to the 2x. Remember to give it the 2 for the chain rule, so I'm going to rewrite that as 60 e to the x minus 2e to the 2x. Let's go straight to the second derivative. The second derivative is 60 e to the x minus 2e to the 2x. Derivative of 2x is 2. Now I have the second derivative is 60 e to the x minus 4e to the 2x. Okay. As always, we want to set this equal to 0. 60 e to the x minus 4e to the 2x being 0. Says, well, they both are divisible by 4, so let's take a 4 out. They're both divisible by e to the x. I'll factor that out. 4 goes into 60 15 times. E to the x is factored out. This 4 is factored out. E to the 2x, if I take e to the x out, I have an e to the x left. This is equal to 0. I need to set them both equal to 0, so I have 4 e to the x is 0. I have 15 minus e to the x is 0. So the first one, 4 e to the x is never going to be 0. But 15 minus e to the x says 15 is e to the x. you can take the natural log of both sides. So the natural log of 15 is the natural log of e to the x, which says the natural log of 15 is x. So this is my only point that's going to split it up. Now the domain, because it's e, is all reals. So I go from negative infinity to infinity. If the natural log of 15, you're thinking, well, how do I split that up? You can go to your calculator, put in the natural log of 15, and it says it's about 2.7. So I'm going to write that in there so we have it. So we are going to split up the real number line. Right here, this is natural log of 15. So we're going negative infinity to the natural log of 15, and then the natural log of 15 to infinity. Okay, we need to pick a point. Well, we know this is 2.7. Why don't we pick something easy like 0, and maybe pick something big like 10. It just has to fall within the intervals. What are we plugging this into? We're going to plug this into 4e to the x times 15 minus e to the x. 4e to the x is always positive. 15 minus e to the 0 is positive. This says my first interval is concave up. Then the 10. 4e to the x will still be positive, but 15 minus e to the 10 is definitely negative. That says concave down. I can see it change concavity at the natural log of 15, which says the natural log of 15 is an inflection point. As always, to get the point, we need to go back to the original and plug in the natural log of 15. So I'm going to write it way up here. So I have the natural log of 15. Here I have 60e to the natural log of 15 minus e to the 2 natural log of 15. Think about your rules. Remember, you can do 60e to the natural log of 15 minus e to the natural log of 15 squared, or you can just put this whole thing in your calculator. 60e to the natural log of 15 will be 60 times 15, which is 900. E to the natural log of 15 squared will be 15 squared, which is 225. 900 minus 225 gives us 675, and this will be our inflection point. Because the number is so big, I think it kind of shows us that even though we have graphing calculators, we still need to be able to do the calculations on our own because it might be difficult to figure out where these numbers are at and to get precise numbers. So that 675 would not normally show up on the screen. You can zoom in, zoom out, but it may take a while to get it.